Everybody. Welcome to, I think, session 2 of this summer school. My name is Pascal, and I'm assistant professor here at the University of Amsterdam. I am unmuted on the laptop. And I'm tasked here to talk about deep learning, intro to deep learning. And I think the plan already says we do a lot of advanced IR topics. So I guess it's the walking before we running session. So I guess for most, there's some familiarity with deep learning or a lot. So let this be, let's say, a refresher or a smooth start, so that for the rest of the week we all speak the same language and we all know what we're doing. So, not surprisingly, I do deep learning. So mostly I look at the geometric foundations of deep learning, hyperbolic geometry, etc. But today we'll talk about the essentials, right? Where did we come from? How did we get here? How does the technicalities of deep learning work? And what does it mean for the rest of the week? Well, if we talk about deep learning being a recent revolution, right, we can be very wrong. Does anyone know from which year this picture is? Wager a guess, maybe? 1990? I think it's about right. Yeah. So deep networks, they are quite old, as we will see. And where back in the day, they could be used for the US Postal Service to recognize individual digits, right? These same networks essentially can do this, right? Where now they can recognize things at a level that we deem quite unprecedented. So all these pixels that you see here are generated from scratch by some generative model. And the question is, how does it work? How do we get here? What is substantially different between what is happening back in the day and what is happening right now? I'll find this one quite. Do we have not sure. Way better, yes. Lovely. So where do we start? So if we want to summarize this entire lecture in one slide, I think this will be it. So if you want the full definition, to me, it's a family of parametric, as things to learn, parameters, nonlinear, very important, hierarchical representation learning functions. Talk about what's the importance of this. I think the one in yellow is the most important part here, which are massively optimized with gradient descent to encode domain knowledge. In other words, solve a task at hand. And typically what we do, we have some input X. We feed it to a series of layers with some stuff in the middle, and then we enter the outputs. And based on that entire thing, we have a loss. That is the essence of it. And I think to explain where this is coming from, we have to go back to 1958. So how to end up at the previous slide, I think 1958 is a very nice starting point. We have to start somewhere. And I want to start with the perceptron. I think Rosenblatt was the person on the right. Right, that was the golden age of science in the sense that the United States just gave a lot of money to a lot of people. You have to work for, in this case, the US Navy to do so, but still a lot of money. And Rosenblatt came up with the following idea. What we could do is if we have some inputs, in this case, n inputs, what we could do is learn a weight for each input, take the sum of that weighted multiplication, feed it into a step function, and to get an output. Very smart. Right, and what this output does is make a threshold, right? Below 0, class 1, 0 and above, class 2. And how it works is as follows. So we set for each weight, for each input, we set this weight randomly. Let's say from a Gaussian. We sample one sample at a time. Take one sample and its label. Compute its output, basically do a forward pass. And this indicator function is basically the step function, below or above a threshold. In this case, 0. If it's too low, increase the weights. If it's too high, decrease the weights. That's it. Quite brilliant. There's already a few ideas here that we will use extensively later on. I think step 2 is foundational. Does step 2 remind anyone of anything? So why do we take one sample at a time? I have the training sets. I have 100 samples. Did I take one sample at a time? Ring any bell to anyone? Instead of normal gradient descent, what is this? Stochastic gradient descent. 1958, we did stochastic gradient descent. They didn't know, we didn't give it the name yet, but one sample at a time. Stochastic gradient descent. Well, gradient descent here with a grain of salt because we have a step function, right? Step function should be straight. What is the gradient here? 0. So gradient here? 0, 0, 0, 0. Very ugly function. So we will excuse Rosenblatt for that, but otherwise not a great function. But he was quite impressed with himself. He made this algorithm and then he presented this algorithm. He said the following: the perceptron is an embryo of an electronic computer that, in this case, the Navy, because this founding body, expects to be able to walk, talk, see, write, and reproduce itself, to be conscious of its existence. Beautiful. It could only solve linear functions, though. So quite a bit off. When he presented it, the Navy was excited. Oh my God, we have all these robots we have in these sci-fi books coming to life now. Unfortunately, none of that was possible, so they stopped giving them money. And I think what Rosenblatt really struggled with is what we struggled with for a long time, and we finally get into grips of it right now, is what is called Moravec's paradox. So if we talk about an AI researcher in, let's say, the 1970s, you ask that researcher, what would be the pinnacle of AI, machine learning? They would say, well, if someone can solve chess. Chess is for us extremely difficult. It takes a lifetime to be able to do well. And if then a machine is better at it, that is perfect. What I show you on the right is the ultimate hubris in this. This is the worst take. This is 1966 as MIT. They had a summer project that essentially solves computer vision in one summer project. One undergraduate student could come and they'd be like, well, maybe you just detect objects, basic objects in an image. How hard can it be? It's easy for us, right? How hard can it be? It turns out that problem solved, but better than humans already decades ago. This one, we can still debate whether computers are as good as us as recognizing visually. If I would say 5 years ago, it would be not even close. So right now we are fully aware that reasoning that is difficult for us requires little computation and perception from sensors a lot. It's not surprising. 50% of your brain power is already devoted to looking and recognizing what you see. So it might look easy for us to recognize that a cow is a cow in the field, but only took a few million years of evolution and 50% of your daily calorie intake, and then it's easy. All right. So there was initially a lot of hype, right? You could solve some basic problems, but they didn't lead to an Armageddon. So a lot of big funding agencies stopped giving them money, and we went on a different route. Interestingly, if you look at a number of these words here, a bunch of the most important things for deep learning were discovered in this era. So what we call now the AI winter, with not a lot of funding and other focus on other research, has actually a lot of progress in AI that we now use. And one, not maybe a paper, but one, let's say, discussion that really put a halt on this is, well, the perceptron is so great. What is the simplest failure case? Does anybody can already guess what the simplest failure case would be? You only need 4 data points. Computer science 101 operating function. XOR, right? If I have circle, circle, cross, cross. Give me a straight line that has 100% performance. There's no way, right? So if I have, let's say, the XOR, this is my data set for the XOR, right? For data samples, 2 labels. You see there's a very small network. Yeah, and good luck. There's no straight line that fits this. So this is 1969. And then we're like, oh, there's something as easy as this we cannot do. So what can we do? Well, if you think about it, there are only 2 solutions. Either drawing a straight line is too simple, or the features are not good enough. That's the only 2 solutions we have. In retrospect, unfortunately for the field, we went into direction 1. Mostly because that's worked out of the box much better. So this is a little bit how then the entire pipeline works. So we have the entire world, and for the problem we have data, and we're going to create features for this data, and for we have the layers, split into train tests, etc. When I was in your place, we didn't talk about deep learning. We talked about SVMs. Half the course, machine learning, was SVMs. Now I teach a deep learning course. It's maybe 15 minutes, just out of a historical perspective. Not really practical. So what we did was we said, okay, you love straight lines. Maybe we can make a little bit nonlinear, but at least it's 1 layer. And the problem is these features. Right? We need to make better features. Better features make our life easier. If at any point we can make a problem linearly solvable, there's no need for all this rest. So what you'll see everywhere is bag of words was everything. I see. You remember, Martin, back in the times, bag of words, everything. In text, this is quite easy to do in the sense that we make a vocabulary of the individual words, and then we can make a feature factor out of them based on, does this word occur or not, maybe how often. We did this a lot in vision. You can find 2 decades of bag of words literature. It went really deep. The first thing we did was, oh, you have images, you make patches out of it, and then you have a feature factor for a patch. Well, then we can cluster them, and then the clusters are then the words, and then we can do assign them to the nearest cluster. And then we can make better features to make better clusters. Actually, we can also make 2nd-order derivatives of these clusters. And we did all sorts of things just to avoid doing deep networks afterwards. We just make better features such that eventually you can give them to a linear layer, SVM, or even something like a random forest, and be happy. One of my first meetings as a PhD student was a crisis meeting. If you remember December 2012, based on the ImageNet, the first deep network that beat the old models was around 2012. So when I started, I learned about SVMs, about SIF descriptors for images. I was very happy. I knew what I was doing. My very first meeting, crisis. University of Amsterdam was 3rd in the world in doing object detection the old way. Top of the line, very proud. And then error rate was halved. Right? So what do? Panic? Do we stick to our guns? We are the experts in this, or do we move? The answer is obvious. We move. You were playing with 1 or 2 percent point down every year, and then 10% point gain. Yeah, that's easy choice. So the idea is, rather than a human deciding how data should look for a machine, we let the machine decide. So we have the raw input itself. And then we say, you figure it out. You make a deep network, you go from input all the way to the output, and only the output decides how to update everything. That is essentially the only difference. And for the rest of, let's say, the first half of it, we'll talk about only about multi-layer perceptrons, so dense layers. The second half, we'll talk about other foundational layers for this. So when we were the first half, we go a little bit over the essentials, right? Forward, activations, backwards. The second part, we'll talk about the more fun stuff. So the idea is that we take this idea of this linear layer and we just stack it. Take a linear layer, another linear layer, another linear layer, etc. And then what we want to do is in the end, we have some label, compare our output to the label and use that error to backpropagate everything. So the very first thing that we come across is that I cannot just stack layers, or I can. It's just a silly thing to do. And I show you this example. If I just let's not even think in higher dimensions. Let's think in 1D. If I have two linear functions, right, where for the first one a and b are parameters, and for the second one c and d, and I stack them, I end up with another linear layer, where now a and c and c, b, and d are, let's say, the parameters. Because they are learned, I gained nothing. If they're fixed, sure, there might be some things going on, but I'm learning things, so I end up with a linear function. So I need to break this problem. I need to break it up. And we do so by adding a non-linearity. So what we do, every neuron, right, that comes into a hidden layer, you make a transformation. Can someone name an activation function? Just curiosity. First thing that comes to your mind. 10x, sure, yeah. Relu. Softmax, that is a compound already, but yeah, I like the direction. Simpler version of softmax. Sigmoids. That was the first thing we tried. Why? It looks really nonlinear, right? More nonlinear. Maybe sounds better. And what we really love is that it's derivative folds. This is a classical exam question. If I take that function, 1 over 1 plus e to the minus z, I take the derivative of it, it's itself times 1 minus itself. Beautiful. Great. We used this for a long while, but there was a problem with this activation. The problem is vanishing gradients. Why do we have vanishing gradient problem? Does anybody see the problem with the derivative? What is the range of the sigmoid? 0 to 1, so somewhere between 0 to 1. Then minus is also between 0 and 1. So I multiply two things smaller than 1, it becomes even smaller. If I do that over many layers, it becomes smaller, 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 smaller. Very quickly, actually. So in the end, we have this thing. Looks a bit uglier, to be honest. But no judgment, but a little bit uglier. So what do? We just take the input, and if it's above 0, it's just nothing. And if it's below 0, we take 0 as the value. Seems like a weird thing to do, but my intuition, I will give you an intuition about why this is a good idea in a little bit. First, gradients are much easier. It's either 0 or 1. Now, this looks not so nonlinear. Well, it's piecewise linear, two linear functions. This looks much more nonlinear, right? Intuitively. I'll show you what the problem is. If I do a range from minus 10 to 10 in this case, looks like this. And then it looks, right? They look close. Now, so what I want you to think about is how can you measure how nonlinear something is? You look by fitting a straight line through it. Now I do the same thing. I do a minus 1000 to 1000. I do it for the sigmoid. Almost a straight line. Now I do the same for ReLU. I can try to do this. It's very difficult. Here it's very easy. So this is how a visualization can trick you. This looks super nonlinear, but in the grand scheme of things, it's bounded between 0 and 1. It's actually not that nonlinear. ReLU is quite more nonlinear, even though it's just two linear functions combined. This thing is quite nonlinear. Just as an intuition for you to consider. I think we discussed this already. So the boundedness of sigmoid, of course, has great use. You will see in a slide or two. And we like the math, so that's why we stuck around with it for a while, but in the end, not the best idea. ReLU is simple and fast. Stronger gradient signal. So hence we use ReLU. Is that it? So we already talked about 10H. 10H is a similar problem as sigmoid. There was a time, maybe 2016, 2017, you could get a lot of citations by making one of the million variants of ReLU. I've seen them all. LU, ReLU, FLELU, Swish, leaky ReLU, sure. They all exist. You do, instead of you do this, you do this. Or some people are purists and they say, well, actually, this is ugly. What if the derivative at 0? Doesn't matter, you can just define it. But if they're like, this is discontinuous, I'll make that continuous version. And all sorts of minor variants, and they show that they're 0.5% point better. And then there were a lot of meta-analyses. They were like, yeah, it's basically the same. So in the end, we went back to ReLU because it's the easiest one of all. Not always the case. So I right now do a lot. I'm checking out implicit representations. It's kind of a weird thing. So given an image, you make it into a neural network. So you give us input coordinates, your outputs RGB values. So you compress it into a network. And then it turns out you want sinusoidal activation functions. Actually, it seems like you're learning some sort of Fourier transform of an input. But so just to point out, it's not always the case. There are special cases where some activation functions are better. But in the broad sense, if you use ReLU, no one will ever complain, and you will likely not get a lot if you use anything else. So the forward pass is quite easy. Linear transformation, ReLU, basically thresholding, linear transformation, ReLU, and we repeat it as long as you want. And then we're at the end. And I have an output. And what I want from an input is that my output matches the label of that sample. Right? If I have a cat versus dog classifier, I have an image of a cat. I want my probability of the cat to be as close as 1. But if I have a regression problem, predict the house price of a house based on some features. I want my predicted house price to be as close as possible to the real house price. So what we do is we compare the output to the label, create a loss, and then throw it back. So this is where sigmoid does come in. So for binary classification, right, we can say, well, we have two classes, you can have 2 outputs, but 2 is a special case. You can also just have 1 output, and the value 0 to be one class, and value 1 to be the other class. And then you can use a sigmoid, where you say, well, if my output is 0, then I have no clue what's going on. So equals to equal probability of either sides. And the more I go towards minus negative, I go to one class, and towards plus. Minus infinity and plus infinity, I go to the other class. And sigmoid will bound this. And then I can create a cross entropy loss. So what do I want? If y equals 0, so class 1, I want to minimize the probability. And if the label is 1, maximize the probability. Right? Go in either direction. And you can maximize this function. We don't like exponents multiplication, so we take, and we don't, so actually 3 things we don't like about this first one. It's maximize something. Right. You can say maximize and minimize is the same, but we, as a field, we said, okay, need some unification, so we do minimization we want. We don't like exponents. And there's some numerical stability issues. To solve this, instead of maximizing the likelihood, we minimize the negative log likelihoods. Minimize negative log likelihoods. Those are the three changes. How do you minimize? You take the minus of it, right? The log of the likelihoods for numerical stability. Yeah. That's it. Yeah. Softmax, we heard in the back of the room already. Of course, softmax, sigmoid. How do you do sigmoid with multiple classes? So you can have multiple outputs, each have a sigmoid. Still works. Needed if you have multiple labels per sample. If you have one sample, so one label per sample, it's actually easier to just have n outputs for n classes, take the exponent of all of them, and normalize. So essentially, what this exponent does, right? If you have even a reasonably small value, it blows it up. So it actually makes it more. It looks at the peakiness of the distribution. You could actually say, technically, I could use a ReLU instead of an exponent. But what an exponent does is really blows it up. So if you look at the distribution over 5 classes, if you have a simple function or a quadratic function, it's more like this. And with an exponent, it's really focus more on one class. There's some overconfidence issues, but it really helps with speeding up the classification to do this exponents. And then, of course, minimize the multi-class concentration. Basically, a sum over all classes instead of 2. Now we have to go back. Right? I'm not going to go all the details. I'm just going to do one example because I think that jogs our memory a bit better. Right? If you go back to high school first, high school math teacher shows you this function. This is some, I don't know, some parameter value. This is some loss. What's the best value? Right? This thing, right? What's the classical trick to get this one? Yes. You want what is nice about this thing is that this value is stationary. So the derivative is 0. The only place where the derivative is 0. That's nice knowledge. So we can take the derivative of my function, set it to 0, and I'm done. Well, we cannot do the same in deep learning, unfortunately. That's the bad news. So we'll do something that weirdly works well. There are some papers on this, and I'm still weirded out. We do gradient descent, which to me is a crazy solution if you think about it. Well, I'll show you some examples. So what you do, you initialize randomly, and you take a step into the percent. So basically, in this case, you initialize some weight value here, and then you look at the gradient descent direction, and you take all these steps until you're here. The idea of deep learning is we do a gradient descent, but then with the chain rule in order. Right? So we have a composite of these modules, and I'll show you with some example because I think it works better than equations. So we have a composite of these loss functions, derivatives, and then we can update the parameters. So I'll show you by example, and then I will talk about why does this even work. But I think an example is a bit better. Let's say we have 2 inputs, one hidden layer with 2 hidden neurons and 1 output. So we have 6 parameters to learn. Doable, right? Let's focus even on 1. So you start by initializing these 6 neurons, given a random value, typically from let's say a Gaussian distribution. And let's say it's a bit small. Hopefully you can see it. So we have, if we take example inputs, 2, 3. We feed it to the entire thing. There's no this is all. It violates my rule number 1, but still, that's for the sample quite easy. We feed it through these 2 layers, 2 linear transformations, and the output is apparently 0.191. Okay. Now, my label was 1. Let's say we have a regression problem because it's a bit easier than the cross entropy. And then we can have this error, right? We have prediction 0.19, label 1. So apparently this is my error. It is greater than 0, so we must do something. We are not happy. So let's say we take parameter 6 that we want to update. So every parameter, its new value, it's its old value minus some learning rate times the error, the derivative of the error to the weight. And the more back in the network the weight, the longer this chain is basically. So for parameter 6, it is the new value is the old value minus a learning rate, so the update step, times the delta of error with respect to W6. Let's check how it works. Okay, you can decompose the error with respect to W6 with from the prediction, from the error to prediction, and from prediction to W6. Now let's fill this in. So we have the error, so we have this loss function, right? The prediction minus actual, so this 0.19 minus 1. And this is the prediction. This is basically the entire forward pass. Now, let's start here, I think. Yeah, let's start here. So I have this entire thing with respect to W6. Well, what is this part? What will it amount to? Yeah, I hear the correct answer very softly, I think. 0. Why? There's no W6 here, right? It can go. And the right part, the derivative of I1 W3 plus I2 W4 times W6 with respect to W6 is see some. Yes, so that is this part, right? Right. AX with respect to X is A. Now the second part, we can take this. Let me take the square. That's why we take half. That is not needed, but we like these small details. X squared becomes 2x minus a half, so it goes. With respect to what is remaining, of course. Let's say we call this H2 as out of simplicity. What we end up with is prediction minus actual times H2. We even call that delta, so the difference, right? 0.191 minus 1, that is this delta, times H2. So what you'll see here is that typically for all the weights, it is a function of what is before and after, right? The input of W6 is H2. The output is this delta, this difference. That's it. That is backpropagation. We can do the same. This is what an example looks like for W1. It is delta times W5 times I1. You can see, right? W1 is a function you see of this. Basically, you see these values of this chain. I1, W5, and delta. So just conceptually, you can always see it's a function of what comes before and after. All right, so let's see if it works. So before I had a delta of minus 0.809. I have an apparently learning rate I set up to 0.05. And these are my old values. I update them accordingly. These are my new values. We feed them in. I think. Oh, yeah. And my new value is 0.26. Success. It was better than before. Before it was 0.19. Now, you can repeat this a bunch of times. In the end, you will end up with an error of 0 for that sample, because you will just go closer and closer to the target value of 1. That's backpropagation. If you want to do this with nonlinear activations, it's just the chain becomes one longer. If you want to do this with classification, you replace the squared loss with the entropy loss, etc., etc. In the end, forward backward is nothing more than linear layers followed by nonlinear activations. Loss at the end, because I have an error with respect to my label, and that error we propagate back. That's it. Now, before we take a short break, I want to talk about gradient descent a little bit. How do we tame this? So just it's a greedy approach, and I think that's what makes it weird. So we initialize some parameters randomly, and we just take updates, gradient descent steps until we're happy. Let's talk about a few concepts. First, stochastic gradient descent. We talked about it very shortly in 1958, but to this day, that's all we do. So what does gradient descent normally do? We take an entire data set, and we take the derivative with respect to the entire data set, and then an update step. Well, good luck doing that with ChatGPT. You have the entire web as your gradient step. That doesn't, right? Or good luck with the entire image data set, fitting it on your GPU. It won't work, right? So we need to take it in steps. So rather than taking the entire data set, we split the data into batches, and we do update steps for each batch. Originally, stochastic gradient descent was for one sample at a time, so that's why some people call it batch gradient descent to differentiate, but they're all flavors of the same thing. Second thing is the problem with, as you already see a little bit here with these red lines, if you take it gradient descent on individual samples or small batches, it becomes erratic. For entire data set, it becomes a smooth thing that follows the curve, but it becomes more erratic. So one thing to tame it is to add momentum. So rather than directly updating your parameter with respect to the gradient, you actually add it to, let's say, a velocity vector, and you update the parameters there. The idea being that if I'm going in this direction, and all of a sudden my next gradient descent is like this, rather than saying, oh, we go like this, use more step like that. So use both the past and the current gradient directions to guide you. So basically, you make your path smoother. Numerically very simple to do by just maintaining an extra factor. But it does really make things much more smooth. Now, there are quite some other considerations. There are also for variance of optimizers. I'm just going to show you a visualization. In the end, setting the right step size is probably the most important thing. A lot of research on line gradient descent. We're looking forward and finding the best step. In the end, we seem to do something like this. Let's get a fixed number. We even have learning rate schedulers, where we say we're going to reset the learning rate or take it down by an order of magnitude. But in the end, it's all about the right step size. Too small, just takes too long, which is annoying. Too big is catastrophic, because I can make my step so big that actually, instead of going towards the bassin, it goes outside, and then you're gone. Now, when should we stop gradient descent? First idea. Very small. And how do we determine that? This becomes tricky. And intuitively, I agree. If I have some minimum or local minimum, I'm going to take until I'm at the minimum. But yeah, numerically, that is always tricky to check out. So in theory, you would say, oh, you continue until we have something that we don't see a lot of difference or anything like this. Now, this is when deep learning gradient descent becomes weird, because if I do that, actually, hard to find this loss function. It always keeps going down a little bit more. And what I see is my test performance going down at some point. I'm overfitting. So these traditional rules of gradient descent are not always applicable. So we typically use a fixed number of epochs, and then we're happy. So what we see is some variance as well. Right, so if you're familiar with it, so we have things like Adam, MS prop. I think you even show Adagrad here. The first thing I like is that the cyan versus magenta. So actually the one that end up on the right is gradient descent, and with momentum, you see momentum just make it slower and smoother, but they end up in the same local minimum. Things like Adam take second order derivatives of these functions to maybe find a better path. But in the end, even Adam is greedy. Now this is weird because, okay, maybe I took the break slide a bit too early, or I'm not sure where they went. I used to have a few extra slides, but maybe I'll just show you. If I maybe to the 3D graph and have all these start here or here, I can end up in very different minima, even though I have a very similar starting points. So it seems very weird to do deep learning when it's so influential, the starting points. Because that's all I can do. I can start, and once I start, I just go in the direction of the gradients. But this visualization already shows you can end up in very different places. And what I want is the global minimum, but how do I find the global minimum in deep learning? My intuition of a landscape is something like this, if I do in 1D. Something like this, right? Where it's like, oh, I need to be here. But if I start here, yeah, the best I can end up is here. Seems horrible. You could say, well, then in that case, in deep learning, what we do is we just sample a lot of initializations, we run it, and then pick the best one. We can do that. But weirdly enough, it doesn't result in one model being 20% accurate and one being 80%. Would be expected, we see this, right? Moreover, in ChatGPT, you cannot train a model 5,000 times and seeing which one is best, right? It's a waste of compute. Somehow it still works. It's very fascinating. One of the leading theories is that actually a landscape in very high dimensional space looks probably more like this. Every local minimum is a global minimum. Apparently. Now, hopefully one of you will figure out in the next 10 years what is going on here. I don't know. But in practice, it just means we can just initialize and be happy. You can reinitialize 20 more times, maybe you get a small improvement. It is not the key, weirdly enough. So it goes against all this old theory of gradient descent. This is the leading theory on this. Every local minimum is a global minimum, or at least close enough. Now I think we do a 5 to 10 minute break. Let's go back at 55 and we'll talk about more advanced parts of deep learning. So what did we do so far? We talked about how we did it in the 1950s. Basically a one-layer network. And how we broke it. And then we went two paths. We made better features and still use the same old school stuff. Or we let the network decide the features. Now that part is very important because these multi-layer perceptions that we talk about for a lot of practical applications, they are pretty useless. So I want to talk about more recent advances and how they make it work. So if the tools were developed in the 90s, activation functions, multi-layer networks, convolution networks, even backpropagation, all these kind of things. What did it take until maybe 10 years ago up till now to make it work? Sorry?
You do hardware
Hardware constraint? Hardware constraint, yes, agreed. Hardware. Data. Agreed. What else?
money.
Why? Why money?
Because you need hardware.
Fair enough. Fair enough. Perhaps you need the killer application for people to invest in your direction. Fair enough. I didn't put it here, but I'll add it. Belief, maybe I will say belief and money comes after belief. course, data is a big problem, right? By the time but then convolution networks were created, you could maybe store 5 images on your hard drive. That's good luck creating a big network out of that, right? So good luck learning from it. So instead of having this free learning, you restrict yourself because there's no data. Of course, networks are nothing more than simple operations that you can parallelize in a big stack, but you need the right hardware for it, like a GPU. I think a very important part here is open source software. Back in the day, what happened was you made a paper, and then you had a baseline. Of course, there was no code for the baseline, so you had to re-implement that baseline. And then hopefully it works as well, and then you try it on your own data. Took you about a month to add one baseline. Right now, you can just look on GitHub, get it done. Also means that if one person makes something, the second person can work on top of it. And especially if you think about working on the fundamentals of it and making it faster, better, stronger, etc., it is key. So only together can we do things, and not like we did 15 years ago, where someone had some MATLAB file that they know because they know the second author and they work together. Then that's how we got it. It was a very weird system where we shared some stuff and then some made a re-implementation that works okay, but that's how it worked, but it didn't make any sense. Of course, tricks. I think the rest of the week, what you see, they're mostly about tricks. ReLU is one of these tricks. Atom is a trick. There's a lot of tricks involved. Dropouts, mix-up, all these kind of terms you might end up seeing. Tricks to make it work. And maybe a bit in line with believing, it's also, sure, if we can have an image of a cow, we can recognize it being a cow, great. But no one cares in the real world, right? If we can do deep learning beyond recognition, generation, segmentation, all these tasks that are very difficult, people will be interested. But let's start at the start, an MLP. I spent 40 minutes on MLPs just to tell you now how often will you use them in real life. Only a little bit. The reason why is this. So let's say I have an image, 224 by 224 by 3. And my first hidden layer has 1024 dimensions. How many parameters will layer 1 have? Don't need to give the final number, but what does it amount to? Sorry? Yes, not even that. Much bigger. No, not even bigger than that. So it's just 224 by 224 by 3 times 1024. That is a lot of neurons. And I'm not savant, I cannot give you the number. Actually, I didn't even, should have maybe pre-computed it. But it's a lot. Not only that, what if the cow was not in the top left, but bottom right corner? Right? There is this locality involved. And locality is key. Locality is in text, locality is in audio, locality is in vision. So we don't want to treat everything as a global thing. We want to have things as a local thing. And that's where the convolution comes in. Key building block in any domain. So let's first talk about convolution in 1D. So what you normally have is a linear layer. It looks like this. So I have my inputs, the dot product with my outputs, and I get one value. So it's a global operation that yields one value as output. The convolution is nothing more than that this thing is a local thing, and my input is in the order, the size of the outputs, with some caveats, but that we'll talk about. So basically what I do is for every input, I look at the window, do this linear layer actually, and then do the output. So the operation is the same, it's still a linear layer, but locally, you do it for every input. And typically at the edges, you either duplicate or get some zeros to make it work. So for, let's say for an image, what do? Input is 7 by 7, filter size is 3 by 3. So I start at the top left corner, do a linear layer. Here, linear layer. So weight 1 times pixel 1, etc. And I go slide over it all together until the end. What is the size of the output? Five by five. Why? Yes. So we started here. You can do this one, this one, this one, this one. So it's 5. If I take a normal image, this is a 7 by 7 image, filled out 3 by 3, my image becomes smaller. Now what we did in the start, we accepted this, and we just stopped at some point because the image was gone. But nowadays what we do is, before we give the image to the convolution layer, to the convolution operator, we artificially enlarge it such that it afterwards is the same size again. So in this case, because it's 3 by 3, you add a ring of 1 around it. If it's 5 by 5, you add a ring of 2, etc., etc. Right, let's test your convolution skills. This is my image. What is my output? Shout. Same. Correct. So what do I do for every pixel? I take 1 of myself and 0 of my neighbors. I get myself back. Who dares? Move to the left. Why to the left? But the thing is to the right. How does that work? Yeah. Exactly. So for every pixel, I take my right neighbor, which means if I'm here, I take everything to the side. Move back. So you're right. 1 pixel to the left, and this means I get a border here because there was nothing there before, and I lose 1 here. Very good. Who knows? Your first instincts. What does this operation do? Anyone? Blur. Correct. For every pixel, I take the average of myself and my 8 neighbors. So it always smooths it. Now this is a tricky one. So essentially, I take -1/9 of all this, the entire block, and then 1/8/9 of myself. So I take more from myself and I subtract from my neighbors. What does this do? In contrast, I hear anyone else? Something in the back. Focus? What do you mean by focus? Very good. Yeah, it enhances contrasts. So actually, it enhances the difference with your neighbors. It enhances contrast, focus, also known as sharpening. Okay, so now with this operation, you can now re-implement Photoshop, the basics of it. All you need is a convolution and the right operator. You can do everything, right? Move the image, make it blurry, enhance the contrast, make it sharper, etc. But of course, fixed convolutions, they are boring. You want to learn them. So what do we do in a convolution network? Instead of having an entire feature vector and then a linear transformation, we have a local feature vector, so a convolution, and we're going to apply it to the entire image. And these outputs are then also, we call them feature maps. You can also see them as images. And then we can do convolutions over them, etc., etc., etc. And maybe at some point, maybe we add some pooling to reduce the size of the image, and maybe have a globe, more bigger view. Some point so small, we like, okay, we make it into a feature vector, and then we do MLPs like we did before. And in the end, we have a cow classifier. And then from all the way from the cow classifier, we go back to all the layers. Now, it's a bit tricky. One thing always took me a while to figure out. So convolution is, let's say we do it on images. So convolution is a 2D operation, which means a convolution that operates in 3 dimensions. Your 2 spatial ones and a channel dimension. If I do it on videos, so I have a 3D convolution network, I work in 4 dimensions. There's always this channel dimension. And a convolutional network works locally on the spatial dimensions and globally on the channel dimension. So let's see. I think this example will make it a bit clear. So I have this 32 by 32 by 3 image. 3 is RGB. Okay, too fast. Okay. And I make a first convolutional layer. So if I have D filters and I add padding, what is the output size? Doesn't matter if they're filters are 5 by 5 or 3 by 3. If I just have D of them, doesn't matter the spatial size. What is the output size of my convolution layers? Anyone want to wager a guess? I think this image already shows you a hint, right? Doesn't matter if it was 3 by 3, if I add padding, or 5 by 5 or 7 by 7. Spatially, every filter I apply over the entire image, but every individual filter creates one image. If I have D filters, I have D images, I stack them. So it becomes 32 by 32 by D. Now, does the output size depend on the input size or the filter size? Okay, maybe I already gave the answer a little bit. What? I think I already said it, right? Doesn't matter if you use 3 by 3, 4 by 4, 5 by 5. It's the input size, right? The size of the input determines the size of the output. Because spatially, I do a local operation. So if I have a 5 by 5 filter for this example, every 5 by 5 filter is actually 5 by 5 by 3. It starts at the top left of the image, does a local dot product with all the filter features and my pixels at that region. So it basically does pixel top left R times the weight in that value. And from all these values, it creates one number, like a dot product does. And then I have the top left of my image of my output. And I slide it over the entire thing. And in the end, because I have data padding, I have one thing of size 32 by 32. I do that D times, so I get a stack of these. Right? So that means there are in total these number of parameters in my layer. Now here comes the trick. Now let's go to the second layer. My input is no longer 32 by 32 by 3, but 32 by 32 by D. Let's say my spatial dimensions are the same. So my new filters are also 5 by 5. By what? I think I heard the right answer already. Here it was by 3. Why was it was by 3? Because the channel dimension at that layer was 3. What's the channel dimension after layer 1? D. I also have D. And then now here, one goes to the top left. All the channel dimensions and that local region. One dot product, one value. And I again repeat the same process. Now I get this for one filter, I get this one back. Now let's say I do B. Still 32 by 32 by B. And I repeat. And now, of course, 5 by 5 by B. And that's how you go over every layer. So in the spatial dimensions, I do locally, and in the channel dimension, globally. One operation creates one value, and then of course that becomes like an image. Does anyone know what's in these images, by the way? What does it look like an image, do you think? Actually, it's more like you can see for images, these filters, what they learn are more like object parts, for example, and these basically become like the detections of these object parts. Because if I have an object part in an image and in my filter, and if they are very similar, you get a high dot product. Basically, like an activation map, right, of these object parts. Now, I talk about images because they're visually the nicest, but they were everywhere. The AlexNet, so the top left one, that started a lot of the hype that we're in right now. But there can also be more videos. Audio, actually before images, it worked really well on audio. You can always say that the first deep learning wave was hype was on audio, but not enough people cared to really make the big splash. Same, of course, with text. If you look about every word embedding model, what did they do? You look at the local context to predict your words and to get an embedding of your words. So very convolutional. Now, and we started making these, and the very first thing that we saw was they didn't scale. At some point I had 10 layers and I make 20 layers and they behave worse than 10 layers. That doesn't make any sense, right? Because I just add 10 layers of identity. It should be the same. So actually I do worse than nothing. Okay, maybe just adding convolutions is very difficult. So we added residual connections. So instead of doing input, convolution, output, we also add a copy of yourself. Basically, what it does is you learn a difference rather than a transformation. And that way we can scale to hundreds, thousands of layers. And all the domains, we try to do all these kind of things to scale it, scale it, scale it. Keeps on linearly improving. We are happy. And now we're in the era of scale. I think a lot of what this entire summer school will be about is about what happens at scale and what can you do. On the left, you see clip. Anyone familiar with clip? That's my own understanding. Few hands. I love clip. What did we do in computer vision before? I had an image, convolutional network, and I have then have a label. The label is 1 of k. This doesn't make any sense. Because I have cat, tiger, airplane. How are they independent, right? It doesn't make any sense. Semantically, cat and tiger are closer than they are to airplane. They are not independent labels. So what does clip do? It says, well, I have an image. Instead of a label, I have a sentence. It goes to its own text encoder. And then they go to the same shared space. So both become a point in space. And then I optimize them to be aligned. So you make semantics a continuous thing rather than a discrete thing. Luckily, the people that made Clip also had 400 million image text pairs. Seems to be very useful, right? And if you train it at scale, it works much better than just classifying things. Right? You will see something that you'll see throughout the rest of the week. I think the next lecture is already on transformers, right? Transformer architecture. Now the question is, I just said that convolutions are the backbone of basically all networks. Might have been a lie. If we did this thing 5 years ago, no one would complain. But now we have transformers. Now you have an entire lecture on it. Very short. Instead of locality being a thing, it's all about global connections. Maybe at a shorter level. MLPs actually are back here. So maybe all of these lessons on MLP are not in vain. I think these pictures we see all over the place, right? We're not just scaling linearly, we're scaling exponentially. But essentially, we're doing the same thing. It is convolutions, it is linear layers. We maybe do it in different ways and different tricks. But it's just stacking these simple things. And we know how backprop works. It doesn't matter if it's 1 layer or 1,000 layers. It's the same principle. But something happens when we do this with billions of parameters and billions of data points instead of millions. And we get all these kind of very nice emerging properties that we'll talk about the entire week. But how do we scale? Let's first talk about, we can just say Oh, well, instead of then we have 1 billion labeled images. Now, good luck labeling 1 billion images. Or 100 billion or 1 trillion images, right? We want to scale further. It's not future-proof to just train images on labels, which is what everything we've been doing in deep learning. We need a label because we need to backpropagate something. Otherwise, what is the point of deep learning? But that's how we work, right? If I go with a toddler to the zoo, they see a new animal they haven't seen before. They somehow can update the representation learning and then later on figure out, oh, that was a giraffe. Oh, okay. Then I attach a label to it. But they didn't need a label a priori. So something that is pretty close is self-supervised learning. So this is normally, right, we have images and labels, and we update our gradients based on the labels. But can we make our own label and then do this forward-backward pass? Turns out we can, and it works pretty well. So what we do is we say, instead of having an image having a label, what I'm saying is more restrictive. So let's say I have 5 images, or maybe I have 3. Normally, I know for each one, I know the label, so I know what should be similar. These ones have the same class. In this case, I'm going to do something more restrictive. I'm saying, well, I take this image, I'm going to make a slight deviation of that image. Maybe I rotate the image, change the colors a little bit. Like slight deviations for which I'm certain that the class that is represented in this image doesn't change. A dog is still a dog if it's upside down, right? So geometric transformations. Then I'm going to say, well, actually, what my task will be is I'm saying these two have the same class and all these are different classes. Maybe not true because there also might be a dog in there, so it might be too restrictive, but at least it gives us a label. These two things are the same. So we call it a proxy task. So we define our own labels based on something that we know doesn't change the semantics and move onwards. And that doesn't require labels. We can just get a huge collection of images and train like that. Just pull and push images based on whether they are from the same source or not. And then once we have this huge network trained, we can have a small data set and then tune it with the labels of those small data sets. But we have this huge collection that we could use to get the right features for our convolutions or transformers. Now for texts, of course, there's a much easier solution. I like this graph. It just shows you the tree over the last couple of years. I cannot keep up. I don't know if you can. Every time you open Twitter, there's new Llama 7 or something. I don't follow. But it just shows you how many people are grasping the idea that what we can do is take a huge network and train it at scale, and things work pretty well. So let me call ChatGPT as an example. I think you will talk about it in more detail throughout the week, but just show you the main idea is what I can do with text is I can use a human as a supervisor. They have made all a huge data sets called the web, talk about their daily lives, some fiction they made, the sports articles, whatever they made, right? A huge collection of things that are likely semantically coherent. I talk about this word in this context. Should there's some correlation that I can exploit? So what I'm going to do is I'm going to train a network on this data. Now, what's my label for a piece of text? I can make one and say there's a topic of this text, but I need a human to annotate a trillion of articles. That's not going to work. I can also take, well, if I have a sentence, I mean, this word, what if I leave it out and I try to predict the words? Just like the self-supervised task. I say I transform the image and that should be the same. Now, of course, there are many variants or tasks that we'll talk about, but you can devise these kind of strategies for free. So you can make your own labels in that regard. And then the entire web becomes your playground. Download the entire web, run these kind of models, huge models, and just feed it all the data. Try to predict, do the same thing. That's all the simple thing we've been doing. Just backpropagate errors, nothing more. Just let it run for half a year on a couple hundred GPUs. Someone checks it every 10 minutes if it doesn't crash. That's all we do. The exact same tools as 1988, except now it's scale. And then we get ChatGPT. Well, ChatGPT, we need something else, right? Because the output is just a model trained on text. ChatGPT is question answering, so we need to tune it to give it answers that we like. Then the human is involved in this reinforcement learning loop. A human is like, oh yeah, I don't like this answer, I do like this answer, you can choose. It's just everything that we know before for decades, trained at huge scale, and then we get models that can write poetry. If someone says this is obvious, I declare them crazy. From any historical perspective, this is weird, because these models, 10 years ago, we were ecstatic that they could differentiate a train from a bus. Now this network can do all sorts of emerging problems. Now, transformers will be discussed at detail. I don't understand them yet. I understand how they work. But as you can notice, I'm in vision, but I don't follow this part, right? I have an image, give it into patches, like tokens, and then I do all this, as you will see, all this attention, self-attention, cross products, and somehow it magically works. Now, I understand convolutions because they are this local operation, basically like detectors of parts, and I may have these activation maps. I get them from text point of view. What you will see is transformers work for everything: text, vision, video, audio. It doesn't matter. Transformers work. And I expect that most will be explained from a text point of view, in which I can follow it. But why they work for everything, I just have to develop my theories there. So where are we now? Right? We just had maybe a high-level refresher on deep learning. We are updating neurons. That's all we do. We have an input, feed it through, look at the difference between my prediction and the label, use that difference to backpropagate. And what we did at the start was develop architectures and these tricks to make them work. First, we changed some layers. MLPs are not the solution for everything. We changed layers to make them fit the data type. Right? A graph network is essentially a convolution network, but then the order of the neighbors doesn't matter. So all these kind of graphs, images, texts, we fit some sort of local network that is scalable. Now, the late stage that we are in right now is we press the scale button of those networks. Maybe we let go of this locality and do more attention-based stuff. Scale data, scale GPUs, run, and then we get these videos that we see at the start. Right? We start to show this generative model. It's nothing more than MLPs stacked on top of each other. So the question now that we have right now is you have these remarkable outcomes, and now what? Right? Does it mean if I scale it 10 more times, we have the final solution? Now this is where we start to disagree with everyone, right? Some people say yes, some people say no. First, we have to acknowledge these nice outcomes and of course test what is not possible here. Right? There's all sorts of things that limit it. It is auto-regressive in LLM, which means I do one word at a time. It seems very restrictive. What about biases? What about causality? Is causality nothing more than seeing everything so much that we just see all the correlation patterns and then we're happy? Or do we have to build in causality? What I do, for example, is hyperbolic deep learning. What I know, everything is Euclidean, right? Linear transformations, non-linears. Now, if I ask you, in real life, everything is hierarchically organized. Problem with the hierarchy is exponential growth. Euclidean space is linear. So no matter what I do, if I try to embed the hierarchy in Euclidean space, I get distortion. So something as fundamental as a hierarchy, which we use for everything, to organize everything from coarse to fine, does not work well in deep learning. So maybe we are happy with what we do, what we can, but I am very confident that there are many things we are horrible at yet. That's good. Otherwise, there's no more research to be done. We're just applied scientists. I think there's a lot more to the puzzle. I think with that though, I want to end this talk. And if there are any questions, please let me know. Thank you.